Hello, and thank you for joining us. Today's webinar topic is Mercury 101, Introduction for Environmental Laboratories. Our presenter is Sarah Kennedy, Applications Chemist for Mercury Products. If you have any questions, please feel free to submit them throughout the presentation or email Sarah directly, and she will follow up with you after the webinar concludes. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Sarah Kennedy.
Thank you, Shelley. So first, I want to thank you all for joining today. Shelley said, my name is Sarah Kennedy. I'm the Applications Chemist here at Teledyne Lehman Labs. And today's webinar will provide you with an understanding of Mercury's unique characteristics, its impact on human health and the environment, and some essential techniques employed in environmental testing laboratories to monitor for mercury contamination. So please be sure to submit any questions you have as you go along, and I'll be able to answer those by email once the presentation has concluded. So let's get started. Mercury is persistent, global, increasing, and toxic. And all of these characteristics make it a health concern and a common analyte in environmental testing. So it will never disappear. It will simply change chemical forms and locations. Sometimes this is due to natural processes and other times because of human activity. Mercury is considered a global pollutant since it can affect the environment in areas far removed from the point of its original release. It is continuously being transported and recycled between its forms as it travels around the world, interacting with the major environmental compartments, the air, soil, water, as well as flora and fauna, including us humans ourselves. And we also know that mercury emissions are increasing, largely due to anthropogenic activities such as the mining industries and the burning of fossil fuels. And while it's common knowledge that mercury is a toxic heavy metal, its toxicity is largely dependent on its speciation, and that's where testing comes in. So environmental testing plays a role in establishing if samples have any mercury, what species are present, and at what concentration. So different mercury species have different physical and chemical properties. Each species also has different mobility, bioavailability, and toxicity. So elemental mercury, mercury 0, is a silver liquid at room temperature. This is what most people picture when they think of mercury, but it's actually one of the least common forms. It's not typical for most people to come in contact with pure liquid mercury. The danger of elemental mercury is actually its vapor form. It really easily volatilizes and is removed from the air very slowly, so it makes it an inhalation hazard. Next, we have the ionic mercury forms. So these are typically mercury salts, such as mercurous or mercuric chloride. The mercurous ions, the +1 oxidation state, are typically found in the environment as dimers for stability. So generally, you'll see all ionic forms of mercury referred to as Hg2. It'll also bond with the other halogens and sulfur as well, like cinnabar ore, which is mercury 2 sulfide. So ionic mercury compounds are water soluble, and they easily attach to particulates in the water. And we also have methyl mercury. So this is the main organic species of mercury. Methyl mercury is formed when ionic mercury is methylated by bacteria at the bottom sediments of aquatic environments. And because methyl mercury is soluble in both water and lipids, it has a higher bioavailability than the other mercury forms. It's also bioaccumulated and biomagnified. So mercury builds up in an individual creature faster than it can be excreted. And it also increases in concentration as we move up the trophic levels of the food chain. And that bioaccumulation is what makes it such a threat to health in the environment. And mercury is ubiquitous and it's always toxic, which is why testing in environmental samples for the individual species is very important. There are some natural sources of mercury. I mentioned cinnabar ore before, so that's what's mined to get mercury directly. It can also be emitted from events like volcanic eruptions, from wildfires, or just natural rock erosion. It can also be emitted into the environment from humans using the mercury supply, so certain products, processes, and other kinds of releases. This can be seen from various industries such as chlorine and caustic soda production. It's also emitted into the air from the burning of fossil fuels, especially coal. And it can be found in everyday products like fluorescent light bulbs, skin lightening creams. It's not really in batteries anymore, but it used to be. Old school thermometers and dental amalgams. And it's also used to extract gold in small-scale gold mining practices. So the mercury is vaporized by heating the amalgam and leaving behind the pure gold. And storage and waste management also needs to be considered and monitored as a potential source for contamination. Once water sources get contaminated, then the mercury starts to accumulate in the fish, and humans eat the fish, and then we're exposed to mercury through our food consumption. So in remembering that mercury is persistent, it's global, it's toxic, increasing, this poses several public and environmental health risks, and therefore is widely regulated. So it's important to limit the mercury exposure to protect human health. As we've talked about, different mercury species have different bioavailability, different toxicity, and it's important to understand the factors surrounding the exposure to determine the potential health severity. So some factors that could affect that are the form of mercury, so what species, the dosage, the age or developmental stage of the person exposed, the duration of the exposure, was it a one-time problem or is it a chronic exposure, and also the route of the exposure, inhalation, ingestion, dermal contact. And some neurological and developmental symptoms of mercury include tremors, insomnia, memory loss, neuromuscular effects like muscle weakness or impaired sensations, and also cognitive and motor dysfunction. So almost all people in the world have at least trace amounts of methylmercury in their bodies. This is kind of a reflection of the prevalence in the environment. However, most people have mercury levels below what's associated with potential health effects. These human biomonitoring studies have established that while most people worldwide are exposed to some amount of mercury, that there are groups that are particularly vulnerable. So these include expectant mothers and their fetuses, young children, and people who are chronically exposed. The mothers with no symptoms of nervous system damage have given birth to infants with severe disabilities. So this suggests that the nervous system of developing infants may be more vulnerable to methylmercury than adult nervous systems. And also mothers who are exposed to methylmercury and breastfeed may also expose their young children through their milk. Some communities are chronically exposed. This includes some indigenous people and small-scale gold miners due to dietary and occupational factors. Communities who practice subsistence fishing and eat significantly more quantities of fish than the general population can be exposed to higher mercury contamination in their lifetime. In the process of vaporizing the mercury from the amalgams in gold mining to leave behind the pure gold is a huge inhalation hazard for those workers. In the United States, nearly all methylmercury exposures occurs through the eating of fish and shellfish products that contain higher levels of methylmercury. So the ecological impact of mercury contamination is global, and the different species are found in different locations. In aquatic environments, we know the ionic forms of mercury can be methylated to create the organic form methylmercury. And methylmercury's ability to bioaccumulate and biomagnify makes it particularly toxic. And pollution of the terrestrial environment and the soil is particularly important as well because it's where we live and it's where we grow and raise our food and our families. So mainly because of that bioaccumulative, mercury contamination is highly regulated. Adherence to the regulatory standards is how we ensure environmental safety and human health. And that's where environmental testing laboratories play their part. Certain industries or matrices have mercury limits established by government regulations. In the United States, these include the Clean Water Act, the Safe Drinking Water Act, the Resource Conservation and Recovery Act, which deals with hazardous waste, just to name a few. And the chart on the right shows the exposure limits set by the National Toxics Rule and the Great Lakes Water Quality Agreement. So in the Great Lakes region, which is where I'm located in Ohio, the limit for total mercury in drinking water is 1.8 nanograms per liter or part per trillion. So it's pretty low. And there are dozens of promulgated methods from government agencies that are approved for testing of mercury. So this chart shows an extensive list that just focuses on cold vapor atomic absorption and cold vapor atomic fluorescence techniques. So each method will specify what is required. So what form of mercury can be tested using that method, the concentration range, it can be really high range or really trace levels, what matrices are appropriate, water, wastewater, coal and combustion, foodstuffs, and what technique, not just cold vapor atomic absorption or fluorescence, but also how to collect the sample, preserve the sample, and digest and analyze the sample. And also what quality control is required to ensure that the data is valid. They also list important things to know, like known interferences for the method, safety issues, what materials you need, how to make reagents, how to mathematically interpret your data. So everything you need is within the methods themselves. So cold vapor atomic absorption and cold vapor atomic fluorescence are the two most common techniques used for mercury analysis in environmental laboratories. So in this next section, I'll first describe the difference between atomic absorption and atomic fluorescence techniques on the atomic level. And then I've got a list of questions to help you decide which technique is best for your laboratory situation. And from there, I'll show you real life examples from my laboratory using the QuickTrace M7600 and the QuickTrace M8000. So I'll follow US EPA method 245.1, which is an atomic absorption-based method, and then 245.7, which is an atomic fluorescence-based method. So let's go into some detail about how each technique works, and we'll start with atomic absorption. So the electrons of the sample are hit with an energy source. In our case, it's light from a mercury vapor lamp. And the electrons are excited from the ground state up to a higher energy level. And when they are excited, they have to absorb some of this energy from the lamp. And the detector on the instrument can monitor that drop in intensity at a specific wavelength. So we measure the decrease in light intensity to determine the sample's absorbance, which can be related to analyte concentration. So that's atomic absorption. So a lot of energy coming in, a little bit of energy coming out. And then atomic fluorescence is a two-step process, and the first step is atomic absorption. You start with your atom, your energy source, in our case the light is shown on the sample, and the electrons are excited from the ground state to the higher state. And when they relax back down to the ground state, they'll release that energy that they took on in the form of light. So for atomic fluorescence, the detector is positioned perpendicular to the incident light source, so it can monitor the increase in intensity coming from the sample itself. And all this is observed at a specific wavelength, and for mercury, this is 253.652 nanometers. So that's atomic fluorescence. It's a much more sensitive technique than atomic absorption. But what technique is right for your lab? So selecting the right technique ultimately depends on your specific analytical needs. For many laboratories, especially those in the environmental sector, the decision will be driven solely by the need to comply with that specific regulatory method. Each method states what technique is required or acceptable. But if your lab is not required to follow a regulatory method, then the driving force for your decision will more likely be the characteristics of your sample matrix and what detection limit you need to reach. And sometimes it also matters if you have a digestion procedure in place. So that's another thing to consider. So this chart is an overview of the two instruments as offered by Teledyne Neiman Labs for mercury analysis. The QuickTrace M7600 operates using the principle of cold vapor atomic absorption. It measures total mercury concentrations in aqueous samples following an online chemical reduction of the sample. The typical instrument detection limit is less than 0.5 nanograms per liter, and it has a usable range between 0.5 and 500 nanograms per liter. We also have a green chemistry tubing harness available to save on reagent consumption, and that widens the range a bit to 0.7 to 700 nanograms per liter. And for the QuickTrace M8000, this is our atomic fluorescence instrument. It also measures total mercury concentrations in aqueous samples, followed by chemical reduction. But it has different modes of operation depending on what calibration range or detection limit you need to achieve. So it has a standard flow-through mode, but it also has single or double gold trap amalgamation mode. So this pre-concentrates the mercury before it's sent to the detector, which allows for ultra-trace detection limits of less than 0.05 nanograms per liter. And the multiple modes also gives it a usable range spanning multiple orders of magnitude, so from 0.05 nanograms per liter up to 400 nanograms per liter. So let's compare some typical methods used on these instruments. So we have US EPA 245.1 and US EPA 245.7. So very similar in name. You know, the numbers are similar. They're both determination of mercury and water. The analyte is the same, total mercury. And the matrices are the same, drinking water, surface water, ground, industrial, wastewater. But they are very, very different in practice. So the highest calibration standard for 245.7 is 100 times lower than the highest one for 245.1. So the ranges don't overlap typically. 245.7 requires a more sensitive instrument, and extra caution needs to be taken regarding contamination in all steps of the process, including the use of different digest chemicals. So for instance, in 245.1, there's only one bullet point in the entire method about contamination control, but in 245.7, there's 3 whole pages about contamination control. So that just tells you a little bit about the sensitivity of the method. And it's also important to note that 245.7 doesn't use gold trap amalgamation. You're gaining that sensitivity just from changing the principal technique from atomic absorption to atomic fluorescence. So that's how we can achieve those trace levels. Cold vapor atomic fluorescence with the gold trap is utilized in US EPA 1631, and it can be ultra trace levels, like a fraction of a nanogram per liter. And that's the most sensitive method for mercury determination, and it's in a league of its own. But I'll save that for another presentation. These flowcharts compare the sample preparation and digestion procedures for 245.1. It's in blue, and 245.7 in green. So they are different in every step of the process except for the sample size of 50 milliliters and the final reduction step of the Hg+2 being reduced to elemental mercury, stannous chloride. So let's focus first on 245.1. Again, this is the atomic absorption method. It's the less sensitive technique. So first, you'll take your 50 milliliters of sample and standard. In this method, the samples and standards are treated exactly the same. They are fully matrix matched. and they are digested together. So first you'll add your acids. You'll do sulfuric acid and nitric acid. And you'll follow that up with a 5% potassium permanganate solution. So in the photo here, you can see that purple color. It needs to persist in all samples for 15 minutes. And if it doesn't, like the tube on the right in the photograph, if it turns like a brown color, it doesn't say purple, then you need to add more potassium permanganate to every single standard and sample for matrix matching purposes. Once you can get that color to hold for 15 minutes, you're going to add your potassium persulfate, and then you're going to do a heated digest in a block digester at 95 degrees C for 2 hours. You'll allow them to cool to room temperature, and then you'll reduce any of that excess permanganate by adding your hydroxylamine hydrochloride. Then you'll vortex your tubes and allow them to stand for 15 minutes. Generally, that last step produces a lot of bubbles. So vortexing just allows your samples to get rid of all that extra gas in your sample. And then you'll reduce the mercury. That's your final step. So here is some data that was collected while I was creating an application note for the M7600. So I was using 245.1 as a base method and using our green chemistry tubing harness and optimizing for those parameters. So I wanted to make a really fast method for the M7600. So as written, the calibration range for 245.1 is 0 to 10 micrograms per liter, but I extended it up to 0 to 20. I just wanted to kind of show off the capability of the instrument. And the calibration curve looked really great. I also used peak area mode instead of the typical peak height mode. And this was allowed me to be able to gain some speed on my run, just eliminate some sample time. And on the left, you can see that for my detection limit study, I used 7 replicates each of a 0.05 microgram per liter and a 0.1 microgram per liter sample. And you see the peak profiles down at the bottom. And my final MDL was 0.021 micrograms per liter, or about 21 ppt, which I found impressive given that the highest calibration point was about 20 ppb. So once my MDL was established, I analyzed the wastewater CRM and chose ERM-CA 713, which had a certified value of 1.84 plus or minus 0.11 micrograms per liter. So my average result was 1.96 plus or minus 0.11 micrograms per liter, so about 106% recovery. And my calibration curve, R squared, was really good. It was 497. My RSC was below 2%, so it's awesome. And my ICV and CCVs are really good. They were at 107 and 106% as well. So everything was looking really good. So let's move on to 245.7. So this is the non-gold, just flow through atomic fluorescence method, and it's a very sensitive technique. So for this, you actually start by adding your acid and your preservative to the tube before you add your sample. It just keeps the mercury in a nice stable form. So you'll add your acid, add your preservative, and then your 50 ml sample. For this, we just digest at ambient temperature for 30 minutes. And for this, the yellow color from the bromine monochloride needs to persist for the duration of the digest. And if it doesn't, you'll add more, same as the other method. And then you'll use 50 microliters of the hydroxylamine hydrochloride to reduce the preservative. This we just kind of invert to mix and swirl for about 5 minutes. Just kind of more gentle on this process than the last one since it is more sensitive. You don't want to be taking the cap on and off and things like that. And the last step is to reduce the ionic mercury into the elemental mercury for detection. So here is data that I collected while I was making an application note on the M8000. This is using 245.7 as the base method, but I extended the range quite a bit up to 10 ppb. So the typical highest range is 100 nanograms per liter. But I wanted to see if the system could retain its sensitivity at low levels while using a really wide dynamic range. So for my method detection limit study, I used 7 replicates each of 0.0035 and 0.0055 micrograms per liter, so 3.5 and 5.5 ppt. And you can see the peak profiles for those off to the right. And my final MDL came in at 0.00040 or 0.4 ppt. So this illustrates just how sensitive this instrument really is. You know, an MDL of less than half of a ppt using a non-gold trap method is pretty remarkable. And this method spans multiple orders of magnitude while still meeting that low water quality criteria set for the Great Lakes region. And for this method, that's 1.3 nanograms per liter was my target, and I was at 0.4. So pretty impressive. So US EPA 245.7 does not use the classic linear regression to determine the concentration of mercury from the fluorescence results. So it uses calibration factors, which is noted as CF subscript X, and it uses blank subtraction as well. So the final concentration of the sample is calculated, you can see it under the chart. It's HF units of the sample, subtracting the average HF units from the system blanks of the calibration, and then dividing that by the calibration factor average for all the samples in the sequence. And there's also rigorous QC requirements for this method. So just for the calibration itself, there's a limit on the maximum blank concentration. There's a limit on the standard deviation of the blank concentrations. There's a % RC limit on the calibration factors themselves, and a % recovery of the lowest calibration standard limit. And then if all of that passes, then you can run your initial precision in recovery, your ongoing precision in recovery, and your MDL. So that's all on top of your typical QC requirements, and before you can even start running any samples. So just really rigorous QC for that super low level 245.7. All right, so I was able to get all that QC to look good, and then I established my MDL. We saw that data earlier. So I was able to run my CRM samples to validate my method. So I had extended the calibration range 100 times higher than the original method. And this application is still able to meet the quality control acceptance criteria, and it exceeded the method detection limit requirement for 245.7. So I used the same CRM as the previous 245.1 method. So my average recovery was 1.85 plus or minus 0.005 micrograms per liter. So it was 100.5% of the certified value. And it's important to remember that when you're looking at low concentrations, mercury is everywhere. So some helpful tips for low-level mercury analysis include contamination controls, and also choosing the right digest is important. So for contamination controls, in my lab I use in-line gold traps that can remove mercury from the carrier gas, also from the gas that I use to sparge my reagents. So I typically sparge DI water, 3% HCl that I use as the diluent to make my stock standards and calibration standards. I also sparge stannous chloride and hydroxylamine hydrochloride. So I sparge all of those before use just to make sure that there's no mercury in there before I begin. I also use reagents marked for the determination of mercury. It's especially important for your potassium permanganate. It loves to scavenge mercury. So you want to make sure from the get-go that you're not adding any extra mercury to your samples. And I also recommend using trace metal grade acids just for the same reason. Anytime you can start with a really low level of mercury, you're going to end up with better results. So we want to limit that contamination. And it also helps to choose the right digest for your matrix. So adjusting the variables of what acid types you use, your heating profiles, and also the the length of time for your digest might make a huge difference in the success of the sample. And sometimes no amount of chemical digestion is going to be enough, and you're going to want to use a microwave system to really break down your samples. And those are just a handful of tips for contamination controls from within the laboratory and some variables that might affect your sample digestion. So again, mercury is persistent, it's increasing, it's global, and it's toxic. And that's what makes it such a health concern and a common analyte in environmental testing. Monitoring the sources and the types of mercury is essential for reducing poor health outcomes for the public and the environment. Standard promulgated methods are available to help determine if the samples exceed the mercury concentration set by those global regulations. Environmental testing labs play a crucial role in understanding how mercury is cycling through the world. And understanding your lab's unique situation is the first step to choosing the right analytical technique and instrument for your mercury analysis. So that concludes my presentation for today. Thank you for listening. Please feel free to reach out if you have any questions. My phone number and my email are listed here. These are also the QR codes to all of our social media at the bottom if you want to give us a follow. And a link to our new website, Teledyne Labs, is up at the top. We'll send out a link to the presentation if you would like to review it in a couple days. And again, thank you for taking the time today to learn a little bit more about mercury analysis.